So the last stop for today is Lawrence Roy, who's going to talk about Softspoken OT.
Hello, everyone. So I'd like to discuss Softspoken OT, a new OT extension technique. So in a one of two oblivious transfer, the sender picks messages M0 and M1. The receiver picks which message, MX star, that it wants to learn. The receiver must not learn anything other about the other message, and the sender must learn nothing at all. However, I'll focus on a variant of this problem called random OT, where the inputs are chosen randomly by the protocol and given actually as outputs. So the OT is just generate some randomness, random messages M0, M1, random bit X star, random MX star. It has to be correlated with each other. So like MX star must match M0 or M1. In the OT extension, we want to turn a small number of base OTs and take a small number of base one of two OTs and turn them efficiently into as many extended OTs as needed. So Softspoken OT also works for one of an OT extension, but I'll focus on just one of two OT in this talk. In our OT framework, the input base OTs are just instead of just one of OTs, two OTs, they're actually all but one OTs. What that means is that so for just two messages, that's actually the same thing as one of two OT. So one of OT is like a glass that's both half empty and half full of water. In general, the receiver gets all messages except for M delta, while the sender does not learn delta. And we follow silent OT and using a puncturable PRF to generate the all but one OTs efficiently. Internally, the OT extension protocol creates a subfield vector OLE. So it's a bit built up to there to define what that means, starting with just OLE. So an oblivious linear evaluation, or OLE, is where the sender learns learns a linear function, f of x equals ux plus v, while the receiver learns a point delta and the valuation w, which is f evaluated at delta. Equivalently, the parties get secret shares of the product of the two values u and delta. So the structure is just two entries in f are multiplied together. If u is forced to just be a single bit, while v, w, and delta are in a larger field, then we have a subfield OLE. So viewing the larger field as row vectors over f2, this computes a single entry times a whole vector at once. And vector OLE is similar, but now it's delta that's reused many times. That is, u, v, and w become column vectors, and the same delta is used for all entries. And then finally, the subfield VOLE combines both of these together. So by working with, so if you're working with vectors and also have u, b in a subfield, and again, if you treat the subfield, the larger field as a row vector, in F2, we see that the outputs are just the outer product of u and the deltas. That is, every element of u gets multiplied by every element of delta, and then there's secret share between the two parties. So this is the correlation, main correlation that gets produced inside a OT extension protocol. So it's a main sub-goal of like the work. So here's a comparison showing how Softspoken OT fits into the main classes of OT extension. So the first main category is the similar OT extension of IKMP to get because of the protocols it expired. So IKMP requires only a correlation robust hash, which is a symmetric key assumption. It also is computationally very efficient, but unfortunately, it sends lambda bits of data for every single OT. So where lambda is the security parameter. So communication is often a bottleneck. The main alternative is protocols based on silent OT, which uses an additional learning parity with noise assumption. But so the communication cost goes way down because for generating L OTs, it only goes up with the log of L in total cost. But on the other hand, the computation is a bit more expensive because it requires the most efficient versions use dual linear learning parity of noise, which require computing the syndrome of random message over a large linear code. And this typically involves solving systems of linear equations. So SoftSpokenOT attempts to bridge the gap. It's structurally similar to IKMP, but it exposes a communication computation trade-off. So for any trade-off parameter K, SoftSpokenOT can improve IKMP's communication cost by a factor of K. But unfortunately, this comes at the cost of using 2 to the K divided by 2K times the computation. So however, since generating bits from a PRG is quite fast and using hardware implementations of AES, this trade-off is beneficial when K is not too big. So continuing with the comparison with IKMP, here's an overview of the steps for OT extension. So some XOR operations are applied to the input base OTs to get 1-bit vector OLEs. These are then combined into a single subfield 2 to the lambda vector OLE using de-randomizations to make all of their U vectors match each other. And finally, each of the L rows of the subfield VO becomes a 1 of 2 OT just by hashing it. The only step in this that requires communication is the de-randomization step. There are lambda bits to de-randomize in each OT. SoftSpokenOT replaces the F2 VOLE with a new subfield VOLE. These VOLs are based on all but 1 OT. Because they output in a field that's K bits at a time, we only need lambda by K of them to get the desired subfield F2 lambda VOLE. Consequently, only lambda by K bits are needed to be de-randomized, which is what reduces the communication. The base OTs generate arbitrarily long strings M0 and M1 using a PRG. So like you can use a PRG to arbitrarily extend a random OT. Because for a random string, it just becomes an extra large random string. And then it turns out that just plain XOR is enough to generate an F2 VOLE from there. Or equivalently, you write it using the all but 1 OT, like SoftSpokenOT will use. If the receiver gets M0, then W will differ from V because one will be M1 and the other is M0. So the difference is now M0 XOR M1, which is U. So that matches delta equals 1. And then if the receiver gets M1, then the V and W will be the same. So the difference is 0, and with that matches delta being 0. So let's plot this computation. So all the variables are defined as linear functions, the messages. So you can plot their coefficients as a function of X, where X chooses which message. So to make a nice diagram over the real numbers don't wrap around at 2. So you can pick signs. So like plus, or some of them will be add, some of them you subtract, chosen to make it the calculations still work out properly. So they make the sign of a number, of course, makes no difference in F2, but it's also useful because it shows that it works for higher characteristic fields if you want that. So the received message W can also be written as such a linear function. And notice that its coefficients have a root at X equals delta. So here in the drawing, delta is 1, which allows the receiver to compute W without knowing M delta, because M delta just gets multiplied by 0. And then, as you can see, the difference between these two lines, W minus V, is -1 everywhere. And that matches here U being -1 and times delta, which is 1. So next step is generalizing this picture to SoftSpokenOT. So U continues to be negative the sum of all the messages. So it's still in the subfield F2 containing all the message bits. V's coefficient continues to be linear, so XMX. And W's coefficient also is linear, but again, it's now its root is delta. So here delta is 3. And then notice that again, the difference W minus V is again always minus delta down here. This is because W has been shifted down by delta in order to make its root be at delta. Therefore, W minus V is always U delta, no matter what the message bits are. So this is a subfield VOLE correlation. So after the subfield VOLE, de-randomization, the next step is de-randomization. So de-randomization is a well-known technique that turns some of the outputs of the correlated randomness into the inputs. In this case, we need to use it to control U. The sender computes a correlation C, the difference between the desired U and the given random U prime, and gives it the receiver. And then the receiver can compute a corresponding correction, which makes the output still be a VOLE correlation. Next step in IKMP is to somehow combine all the lambda F2 voles into a single F2 lambda vole, subfield VOLE. Here are the F2 voles all written out independently. So we need to randomize all the U vectors to be the same. Is needed because for a subfield VOLE where each, this is needed because for a subfield VOLE, each entry in U must still be only a single bit. This costs lambda bits for each OT, again, because there's lambda of these things. So now we can stack all of them side by side nicely, now that all the U's are the same. So if we stack them side by side and interpret each row as like a member F2 lambda, then this becomes a subfield VOLE. And for SoftSpokenOT, the step is virtually the same. However, the input is only lambda by k of these subfield voles instead of lambda voles. And so because there's only lambda by k of them, it requires only lambda by k bits per OT. Otherwise, it's the same. And then the final step is hashing. So the VOLE outputs, each row in these VOLE outputs are hashed to get the OT messages. So either U will be 0, in which case V will equal W, and so M star will be M0 here, or V will be 1, and then M star will match, MX star will match M1. So hashing these numbers so hashing these things strengthens the entropy because so the other one of these two messages will be unpredictable, and then the hash function will be impossible to find the right pre-image. So the hashing these turns it into random OT messages. However, notice the sender got to choose which message to get. So this was the sender, yet it got X star. This is a choice bit, it should be the receiver, right? So this means that that's a property of IKMP style OT extensions. They swap the roles of the two parties. So I'll continue using the words sender and receiver to refer to the base OT sender and receiver. So far, these protocols are only secure in the semi-honest model. When the base OT sender behaves correctly, we get the correct result. An outer product between the U's and the deltas. That is, some of the rows of W minus V will have all the deltas, and some of them will have none, all these zeros. Nothing will be in between. What happens if a malicious base OT sender decides to lie when de-randomizing its U? It could, for example, make the U's into be like an identity matrix, isolating each of these deltas in its own row. Now, from the sender's perspective, there's only one bit of entropy for each of these rows. So if they learn the extended OT message, there's only one bit that they don't know. So they can just try both options to hash, see which one matches, and learn that individual bit of delta. And then once they learn all the bits of delta, they learn everything. So that breaks the OT extension. So that's the standard attack. The standard fix is consistency checking. So I'll present a simplified version of the SoftSpokenOT consistency check, which is similar to the OOS consistency check. So a consistency check, part of the correlation is revealed and checked to be consistent, while the rest is kept secret to be the actual real output. So more precisely, multiplication by a matrix preserves this correlation property that we're trying to build. So the base OT receiver should generate a random matrix R, and they should check that RU, RV, and RW satisfy the VOLE correlation here. Forcing the last S rows of R to be the identity matrix guarantees that when at the end you burn the last S rows to preserve the secrecy. That really does make sure that these values here, U tilde and V tilde, didn't actually reveal anything important. So there's this parameter S that controls how many rows are in this matrix R, how many checks are performed. So it controls the chance the adversary can accidentally break the scheme. It's like a statistical security parameter. There are several malicious OT extension protocols based on OT consistency checking. So here's a comparison. So they make it apples and to apples. These are all been instantiated using just for one of two OT, even though some of these are for papers that were considering one event OT. So the consistency checking protocol for in CCG is very similar to ours. However, our proof is slightly tighter bound, which allows us to have the number of rows sent in the check. But unfortunately, for the other main OT extension, mostly secure OT extension papers we considered, there were flaws. So for OOS, it was just a flaw in the proof. And a special case of the SoftSpoken OT proof also shows that OOS is still secure. We found a couple different attacks on KOS and not really sure what the extent KOS is attackable. One is just kind of a trivial thing. There was some collision that they didn't consider, and it only violates some lemma. But there's a real kind of interesting attack where in the very special cases on what the security parameters, what the field they're working with is, it can attack it with complexity 2 to the lambda by 5 in a situation that it should be 2 to the 2 lambda by 5. And then finally, I found an attack on PSS that's like actually a practical attack. So for lambda chosen to be 128 and the right choice of A, it can break PSS of probability 1 over 256 using only 2 to the 18 hash evaluations. So how does PSS differ from OS? So they're very similar, except for PSS tries to compress their consistency check. The way they compress it is does not make sense in terms of finite fields. So again, let's treat F2 lambda as some row vectors of length lambda. So to emphasize this difference, V and W are now capitalized as their matrices. So to compress the consistency check, what they do is they add all the columns of V together when doing the check. They in other words, they multiply on both sides of the consistency check equation. They multiply on the right by 1, 1, 1, 1, 1. So unfortunately, this compression is vulnerable. So in particular, it allows us to, instead of having to guess individual bits of delta, only have to guess the sum of several bits of delta. So recall that W minus V, again, comes in this form, product of these U's and deltas. So if we, similar to when you had a no consistency check where you did where there's an identity matrix was the attack, but here it's like several bits in a row of 1 instead of just individual ones on each row. So that turns into a few deltas here, a few deltas here, and so on. So this is where if we divide up the deltas into A groups, each of n elements. So here n is 3. So then the main values looking at the consistency check are W minus V times these ones. Well, the ones mean that the one vector means that these deltas only cares about the sum of them. So it ends up being like this. So particular only cares about the sums of each of these groups of deltas. So if we set U tilde equals 0 so that this passes if and only if this thing is 0, then it passes with probability 2 to the minus A, as each group is randomly independent. And then finally, each of these rows is isolating these bits of delta. It's not the full randomness. And so we can recover all of delta by going through and just brute forcing each piece. So there's only 2 to the n minus 1 possibilities for each of these pieces of delta. And then again, if you brute force all of delta, it breaks the whole thing. So finally, we implemented SoftSpokenOT in the libOT library and benchmarked to compare with these leading OT protocols. The parties each run single-threaded on its own core of a dual-core processor, and you have 3 network settings. One is where the bandwidth is unlimited, another is on a LAN with a 1 millisecond latency and 1 gigabits per second, and one is on a WAN wide area network with 40 milliseconds latency and 100 megabits a second bandwidth. So these times are all for generating 10 to the 7 OTs. So in each column, we mark the best and the second best with bold and underline. So in the LAN and local host settings, SoftSpokenOT is like significantly better than the other protocols. But in the WAN setting, it takes second place to Silver, which is a version of SimonOT. Citation of SimonOT. And then the overhead of the maliciously secure versions is low. So finally, if you prefer a visualization of these numbers, here's a chart showing the performance on a log scale of nanoseconds per OT. So the SoftSpokenOT entries have been consolidated, choosing the best K for each. So thank you. That's my talk. Do you have any questions?
All right. Is there a quick question? I think we have time for one.
These are consistency checks where you do random sums that use quite extensively in various protocols. Do you think it's like a systemic issue that people have messed up, or is it just specifically these protocols?
I haven't looked at it closely for other protocols, but I should mention that CCG protocol that was secure, that was based on rather than like coming up with their own consistency check, they built it off of, they basically just plugged in a consistency check for UC homomorphic commitments, and that paper had a good proof and was strong. It's a good start. It had a correct proof. So if other things are using that paper, then maybe they're fine.
Okay, maybe Thomas.
So in your implementation, you said you're using ASNI probably.
Yeah.
All PRS. So maybe you want to look at vectorized AS operations.
Yeah.
AS, where you can run multiple AS instances.
I put a lot of effort into vectorizing it to get those numbers. There is like a thing with like, it seems a little like systems research in a way when you're like, you're optimizing it to try and make sure that your system is better than everybody else's, right? So anyway, I was putting.
The trade-off is interesting. You have this exponential number of PRG evaluations where PRGs also instead of the hardware.
Yeah.
Vectorization all over the place, and this is the current trend in hardware.
Yeah.
So this is a good trade-off.
Yeah.
Cool. Then let's thank both David and Lawrence again.